Have you ever, stood in a room, maybe at a concert hall or just in your own living room with the stereo cranked up, and you notice something kind of strange?
Oh, you mean like when the bass just completely overpowers everything in one specific spot?
Exactly. You hear this low, booming bass note, and it sounds incredibly loud in, say, the back corner. But then you take just two steps to the left, and that exact same note practically disappears.
Right, it just vanishes. It's such a weird experience.
It really feels like some kind of invisible magic.
Hmm.
But that magic, the actual physical reality of how sound behaves in the space around you, is exactly what today's deep dive is all about.
It's one of those fascinating everyday things. We experience it all the time, but the underlying mechanics, like the actual geometry of the air around us, are completely hidden.
So, for you listening, we've got a really specific mission today. Consider us your personal study companions.
Yeah, we are tackling a pretty dense 15 slide collegiate level presentation on wave mechanics.
Right. And it's the kind of physics material that can easily feel, well, overwhelming. But we're going to walk through it step by step. Our goal isn't just to help you memorize a bunch of formulas for an exam.
No, not at all. By the end of this conversation, you're going to truly understand the why and the how behind wave resonance in normal modes.
Okay, so let's jump right in. We are starting on slide one, the title slide, wave interference and normal modes. And it kicks off with a brilliant visual.
It really is. It shows these overlapping concentric circles, almost like you just dropped two pebbles into a perfectly still pond side by side.
Yeah, and those ripples expand and eventually they crash into each other. That visual sets the stage for everything we're talking about today.
Because the foundation of all acoustic physics is basically just what happens when waves collide.
Exactly. Which brings us to slide two. This introduces something called the principle of superposition.
And look, the formal definition on the slide can look intimidating. You've got y1 of x and t moving right with the negative k's, and y2 moving left with the positive ax.
Yeah, the math is a lot.
But the core idea is wonderfully simple. When two waves occupy the exact same space at the exact same time, their effects just add together.
So to ground this, let's use an analogy. I don't want to stare at algebra.
Yeah.
Think of algebraic wave addition,
Hmm.
where y equals y1 plus y2, kind of like merging bank accounts,
Oh, I like that.
right? Like sometimes positive deposits stack up and you have a ton of money. And sometimes, a massive debt perfectly cancels out a deposit, leaving you with absolutely nothing.
That's a great way to look at it. And moving to slide 3, that alignment is what entirely dictates sound. This slide contrasts constructive and destructive interference.
Okay, break that down for us.
Sure, so constructive interference is when the crests of the waves align perfectly. In terms of distance, the path difference is a whole number of wavelengths. 1, 2, 3, just an integer, nm times lambda.
And lambda is just the wavelength, right?
Exactly. When that happens, the waves stack up and the sound gets significantly louder. But then you have destructive interference.
Right, the debt in the bank account.
Yeah, this is when the crest of one wave perfectly hits the trough of another. The formula here is that the path difference is n plus 1 half lambda, so they are exactly half a step out of sync.
Okay, wait, I have to push back here for a second
Yeah.
because looking at the absolute cancellation shown on this slide, it's mind bending.
Mhm.
It's saying that if you add two incredibly loud sound waves together in the exact right misaligned way, you get total silence.
I am. I know it defies common sense.
Yeah, it completely does.
Because we think of sound as physical stuff piling up in a room. More stuff should equal more noise.
Right, exactly.
But sound isn't stuff, it's a wave of pressure moving through a medium like air. If one wave tells the air particles in a specific spot to push forward with maximum force,
Uh-huh.
and the second wave arrives at that exact same spot, telling those exact same particles to pull backward with the same force, those forces cancel completely.
Wow, so the air particles just sit there.
They literally don't move, and if the air doesn't vibrate, your eardrum doesn't vibrate, you get perfect silence.
That is just wild. Okay, let's move to slide four because this actually walks us through a real world application of this spatial interference.
This is a classic setup.
Yeah. So picture this. We have two identical speakers, speaker A and speaker B. They are exactly 2.0 meters apart. Let's say speaker B is stacked on top of speaker A.
Okay, got the visual.
Both are blasting the exact same continuous tone at 784 hertz. And for the math, the slide says the speed of sound today is 344 meters per second.
Standard room temperature physics.
Right. So imagine you're holding a microphone and you're walking along the x-axis straight away from the bottom speaker, speaker A.
Okay, so to figure out where the loud spots and dead zones are, we have to find that path difference we just talked about.
How much further the sound from the top speaker travels compared to the bottom one?
Exactly. So let's look at the math here. The distance from the bottom speaker is just x. We'll call that R1.
Straight line distance.
Right. But the sound from the top speaker, R2, has to travel on a diagonal. So we use the Pythagorean theorem. R2 equals the square root of 2.00 squared plus x squared.
Okay, making a right triangle. I'm with you. And we know the wavelength lambda, right?
We can find it. Speed of sound 344 divided by the frequency 784. That gives us a wavelength of about 0.439 meters.
So on the slide, it shows that setting the path difference, R2 minus R1, equal to exactly one wavelength gives us our first constructive loud spot.
Yeah, and when you crunch that algebra, you find that loud spot is at x equals roughly 4.33 meters.
But then for the destructive dead zone, we set the difference to half a wavelength.
Right, 0.5 times lambda. And solving that shows total silence at x equals roughly 9.0 meters.
So you can be standing 9 meters away with two speakers blasting at you, and the microphone picks up nothing. Unbelievable.
It really is.
Well, let's transition a bit because slide 4 was all about waves traveling freely through open space. But moving to slide 5, we ask, what happens if a wave is trapped between boundaries and bounces back on itself?
This is where we get into the anatomy of a standing wave.
Which is such a cool concept.
It is. So a standing wave happens when an incident wave, the forward-moving one, and its own reflection overlap continuously. It creates a perfect continuous superposition.
And the slide shows these very distinct features.
Right. It defines nodes, which are spots of absolutely zero displacement. The wave just never moves there.
Permanent destructive interference.
Exactly. And then you have antinodes, which are the spots of maximum amplitude, the biggest constructive interference.
Okay, moving to slide 6. This one is titled The Mathematics of the Standstill. And I'm not going to lie, it looks a bit intimidating.
So a lot of trigonometry.
Yeah.
Sure.
They apply a trigonometric expansion sign of a plus or minus b to get this final equation. Y of x and t equals 2a sine kx times cosine omega t.
Which is quite the mouthful.
It is. But here's my question, or my pushback, really. In the first equations on slide 2, we had x and t mixed together inside the parentheses to show movement through space over time.
Right.
But here, they're completely separated. You got the x part, then the t part. Did the wave just stop moving forward?
That is an amazing catch. Yes. That separation is the mathematical proof of a standing wave. The forward momentum is gone.
Wow, really?
Yeah, the amplitude, the 2a sine kx part, is strictly locked to a physical position. It only dictates how tall the wave can get at a specific spot.
And the time part?
The cosine omega t part just says that this fixed shape is oscillating up and down in time. Space and time are totally isolated.
So the energy is just trapped.
Completely trapped.
That makes so much sense. Okay, moving to slide 7. How do we pinpoint these spots?
Well, the math tells us. Nodes happen when sine of kx equals 0. If you work that out, it means nodes occur at distances of n times lambda over 2.
So every half wavelength.
Yep, and antinodes happen at the extremes, where the sine function hits 1 or negative 1. That occurs at n times lambda over 4, but only for odd values of n.
Okay, I need to visualize this.
Mm-hmm.
Moving to slide 8. Let's apply this to a guitar string.
Perfect real-world example.
The slide gives us a string where the wave travels at 143 meters per second with a frequency of 440 hertz.
So first, we find our wavelength. 143 divided by 440 gives us a lambda of 0.325 meters.
Okay, and since the ends of the guitar string are tied down, they have to be nodes, right? They can't move.
Right. So we use our node formula. We map the first 3 physical zero movement spots on that string.
So n equals 0 gives us 0 meters, the bridge of the guitar.
Exactly. Then n equals 1 gives us half a wavelength, 0.1625 meters.
And n equals 2 is the full wavelength, 0.325 meters. So if you lightly touch the string at exactly 0.1625 meters, it wouldn't stop the note.
Because you're touching a spot that's already sitting completely still. That's actually how musicians play natural harmonics on a string instrument.
Ah, that's so cool. Which perfectly sets up our next transition. Because if the ends of a string absolutely must be nodes, the string can't just vibrate any random way it wants to.
Well,
right?
it has strict rules.
Moving to slide 9, this introduces normal modes and the idea that the string is quantized.
Quantized just means only certain specific states are allowed. The wave has to fit perfectly between those 2 fixed endpoints.
So break down these modes for us.
The simplest way it can vibrate is just one big arc across the whole length. We call that the fundamental, or the first harmonic.
Okay.
In that case, the physical length of the string, L, is exactly half of a wavelength. L equals lambda over 2.
But it can also fit a full wavelength, right? Like an S shape.
Exactly. That's the first overtone, which is also called the second harmonic. Here, L equals lambda, and it just keeps going. The second overtone or third harmonic is L equals 3 lambda over 2.
And the slide gives a master equation for this. Frequency Fn equals N times V over 2L.
That formula governs every note a string can naturally play.
Okay, moving to slide 10, the presentation turns this into a sort of detective game, deducing length from successive resonances.
I love this kind of puzzle.
Me too. So here is the setup. A fixed string has successive resonance wavelengths of 0.54 meters, which we'll call the nth harmonic, and 0.48 meters, which is the n plus 1 harmonic. We have to find the length of the string.
Okay, so we know both of these wavelengths have to fit the exact same physical string length, L. So we can just divide the formulas to solve for n. We set up a ratio.
Because if you set up the ratio, the length L completely cancels out of the equation for a minute.
Exactly. You get n divided by n plus 1 equals 0.48 over 0.54.
And doing some quick algebra, the ratio of 0.48 divided by the difference between them, which is 0.06. That means n equals 8.
Spot on. They are the 8th and 9th harmonic.
And once we know it's the 8th harmonic, we just plug it back in. 8 halves of our 0.54 meter wavelength gives us a total string length of 2.16 meters.
It's quite the string.
Yeah, I was going to say a 2.16 meter string makes for a ridiculously long instrument, like maybe a giant cartoonish upright bass.
Hey, the physics works exactly the same no matter how big it is.
True, true. All right, so strings are really easy to visualize. You can see them curving. But what about invisible air, like inside a flute or an organ pipe?
That's where things get a bit unintuitive.
Yeah, moving to slide 11, we hit what they call the acoustic paradox. And I'm going to need your help here because I read this and my brain short-circuited.
Let's hear it.
It says a displacement node, which means zero movement, is a pressure antinode, which means maximum pressure.
It sounds contradictory, I know.
Yeah. How can zero movement mean maximum pressure?
Okay, so you have to remember we are talking about longitudinal waves now, not up and down waves like a string, but back and forth waves, compressions in a gas.
Right. Pushing and pulling.
So look at the visual on the slide. It shows a speaker pushing gas over some powder in a tube. When air particles get pushed against a solid boundary, like the closed end of a tube, they can't move forward. The wall stops them.
So that's the displacement node, zero physical movement.
Exactly. But because they are trapped there and the wave is still actively shoving more air particles into them from behind, they pile up, they compress.
Oh, I see.
Zero wiggle room equals maximum compression.
All right.
And maximum compression means maximum pressure. So a displacement node is absolutely a pressure antinode.
That is brilliant. It's like a traffic jam at a dead end.
Exactly.
All right, moving to slide 12, they apply this directly to organ pipes, and there are two main types.
First, you have pipes that are open at both ends.
Okay.
Because both ends are open to the room, the air can slosh in and out freely. So you have pressure nodes, meaning normal room pressure at both ends.
And structurally, that makes them behave mathematically just like a string fixed at both ends, right?
Yes, the symmetry is the same. So all harmonics are allowed. 1, 2, 3, 4. The formula is Fn equals n times V over 2L.
But then there's the stopped pipe,
Right. Closed at one end, open at the other.
and that completely changes the game.
It does. The closed end forces a displacement node, a high pressure zone, but the open end forces a pressure node. Because the boundary conditions are mismatched, an even number of wave segments can never perfectly fit inside.
So it only allows odd harmonics,
Yep.
1, 3, 5, and so on.
Exactly. And the formula changes to Fn equals n times V over 4L.
Okay, so moving to slide 13, the presentation hits us with a complex acoustic pipe design problem. And honestly, it's a massive logic trap.
Oh yeah, professors love this one.
So here's the setup. We have a stopped pipe with a fundamental frequency of 220 hertz. Speed of sound is 340 meters per second.
Finding the length of that stopped pipe is easy enough.
Yeah.
L equals V over 4F. So 340 divided by 4 times 220.
Which gives a length of about 0.386 meters.
Right.
But then the trop says, the second overtone of this stopped pipe is exactly equal to the third harmonic of an open pipe. Find the length of the open pipe.
And here's where students mess up.
Exactly. I want to highlight this logic step because if you see second overtone and you multiply the fundamental by 3, you fail.
Yep, because as we just established, a stopped pipe only has odd harmonics.
Right. The fundamental is the first harmonic, the first overtone. The next available note is the third harmonic.
which means the second overtone.
Is actually its fifth harmonic.
Exactly. You skip the even numbers completely.
So we take our 220 hertz fundamental, multiply it by 5, and we get 1100 hertz.
And now you equate that 1100 hertz to the third harmonic of the open pipe.
Right. And since open pipes use the normal formula, we do 1100 equals 3 times 340 over 2L. When you solve for L, you find the open pipe's length is about 0.46 meters.
If you hadn't caught that odd harmonic rule, your pipe would have been built completely out of tune.
Completely useless.
Uh,
Okay, moving to slide 14. This feels like the climax of the presentation. It's the acoustic blueprint master table.
it really is a grand synthesis of everything.
We've covered so much physics, but this table brings it all together. What is the ultimate takeaway here?
The grand rule is that boundary conditions entirely dictate everything. Period.
Wow, just the boundary.
It's just the boundaries. If you have node to node like a fixed string or antinode to antinode like an open pipe, the symmetry allows all mathematical multipliers 1, 2, 3, 4.
But if it's mixed,
If it's node to antinode like a stopped pipe, that asymmetry physically bans half the waves from existing. You only get odd multipliers. The physical constraints dictate the math, which dictates the sound.
which perfectly leads us to the final slide, slide 15. The concluding text here is actually really beautiful. I'll just read it. Whether vibrating across a carbon fiber guitar string or resonating through a 32-foot cathedral organ pipe, the behavior of waves is universally governed by boundary conditions.
It is so poetic. Space dictates the geometry. Geometry dictates the frequency. Frequency creates the sound.
That is just an amazing way to summarize the journey. We went from abstract algebra of two waves crashing on slide 2 all the way to understanding how physical space forces waves to create specific, beautiful music.
It really highlights how deeply interconnected math and physical reality are.
Okay, so to you listening, congratulations. You just survived a very real, very dense collegiate level physics deck.
Seriously, well done.
You've mastered the math of resonance. You know the rules. But before we wrap up today's deep dive, do you have a final thought to leave everyone with? Something to kind of chew on?
Actually, yeah, I do. It's something that kind of pushes this whole concept to the absolute extreme.
Oh, I'm ready.
So, we've been talking about guitar strings and air inside organ pipes. But if you look at modern quantum physics, it tells us that all matter in the universe is essentially made up of wave fields,
Okay.
like the electron wave orbiting the nucleus of an atom. It is physically confined by the boundaries of that atom. It can't just exist anywhere. It is quantized, exactly like our guitar string.
Wait, really?
Yeah. So the provocative thought is this. Are the atoms that make up your body, the cells, the structure of you, just microscopic standing waves?
Oh my God.
Is all physical reality literally just normal modes that are trapped by the boundary conditions of the universe itself?
That is. Wow. I'll be thinking about that all day. We're just a bunch of quantized standing waves.
It's all just boundaries and resonance.
Well, on that mind-bending note, we're going to wrap up. Thank you for joining us as we explored this presentation. We hope this deep dive made the math a little less intimidating and a lot more real for you. We'll see you next time. Keep asking questions and keep exploring the physical world around you.